All right, this is part 3 of using the solubility product constant, or our KSP, to in equilibrium situations. So far we have talked about our KSP value is when we are looking at, it's an equilibrium constant for an equilibrium that is happening between a solid substance and its dissolved ions in solution. So remember that it's a dynamic equilibrium, and that what is happening macroscopically, so at eye level we can't see any changes, but if we could zoom in and look at the particles, we would see that there is an equilibrium happening where some of the solid substance is dissolving into ions, and at the same rate some of the ions are precipitating back into the solid substance. So we have learned how to calculate KSP using solubility information. We have learned how to determine solubility using KSP. And we've determined how to predict if a precipitate will form. So how to predict if the reverse reaction will occur and we will get precipitate forming. So if we'll get that equilibrium, and that is comparing KSP to our Q, which is something we already know how to do. Now, today we're going to look at something called the common ion effect. So this is when we are dealing with a solution, and we are applying Le Chatelier's principle. So common ion effect is when the equilibrium of a solution is shifted. Okay, and there's two different ways that the equilibrium can shift, and we'll look at both of them. So the first one is something that we've actually kind of seen already in Le Chatelier's principle. It's when a compound that will react with the ions that are already in equilibrium. So if we add a compound into our solution that will react with the ions in equilibrium. Okay. Now, in my example here, I have sodium chloride solid, and it is in equilibrium with a sodium ion and its chlorine ion. And what ends up happening, so in equilibrium, I'm just going to remind you that it's our sodium here. So our sodium is in equilibrium. Sodium solid in equilibrium with its sodium ion and a chlorine ions. Now, if we were to add silver nitrate, so if we add silver nitrate right here, the silver nitrate is also going to form an equilibrium with its dissolved ions. It's going to dissolve into our silver ion and our nitrate ion. But what happens is we know that these ions are all in an ion party in solution, and they're bumping into each other and colliding. And if they collide and they form something soluble, they redissolve. But we know that if silver and chlorine collide together, they make an insoluble solid, silver chloride. So when the silver and the chlorine combine together in this solution, what happens is the silver chloride solid forms, and it is, because it's insoluble, it makes a precipitate. So by forming a precipitate of silver chloride, it's removing chlorine ions. So it's removing chlorine ions from the equilibrium. Remember, it's removing, the equilibrium is the sodium chloride equilibrium here. So if the chlorine ions get removed by forming a precipitate with the silver ions, the equilibrium is going to shift right to try to counteract that stressor to the system. So all we're doing is applying Le Chatelier's principle that you already know mathematically. So we're going to look at what happens mathematically in a minute. Okay, so the first one is that we add the compound, and the compound reacts with the ions in equilibrium, removes one of the ions from the equilibrium, and so we get a shift because there's a stressor to the system, and the system is going to react to counteract that stressor. Okay. The second way that we can shift the equilibrium is by adding a common ion. So sorry, you should probably pause and make sure you have this part 1 down here. Okay. All right, part 2. So the other way that we can shift our equilibrium in a system is adding another compound with a common ion. So again, we are going to deal with our equilibrium system right here of our sodium chloride is in equilibrium with its ions, sodium ion and chlorine ion. And we're going to add hydrochloric acid. So by adding hydrochloric acid, what we know is that our hydrochloric acid is going to dissociate into hydrogen ions and our chlorine ions. Now, there's no reaction happening here. There's no precipitate forming. None of these ions, all these ions right here that are in the ion party, none of them are going to react and form a precipitate. But what we've done is we've increased our chlorine ion concentration. When we've added our HCl and it's dissociating, we now have significantly more chlorine ion in the solution. So again, you've applied a stressor to the dynamic equilibrium, and our equilibrium shifts left, and we end up precipitating some sodium chloride. So the equilibrium system is reacting to the fact that it now has a lot more chlorine ions than it did before. Okay, so the equilibrium of our sodium chloride in equilibrium with our sodium ion and our chlorine ion is going to shift left towards the sodium chloride to counteract the fact that we have added chlorine ions. So let's look at an example. Actually, hold on. Here we go. So if we use a common ion, this is actually done in industry to decrease the solubility of a compound, to make it dissolve less. Using a common ion to decrease the solubility of an ionic compound is called the common ion effect. So we're going to look at an example, but make sure you have this copied down into your notes. We'll see how this works out mathematically. So now all we're doing is we are combining something we know about Le Chatelier's principle and how to calculate concentrations at equilibrium. So 2 things you already know how to do. We're just combining them together. Here's our example. We want to know what is the molar solubility of PbCl2, so lead 2 chloride, in 0.2 mole per liter sodium chloride solution if the KSP of the lead 2 chloride is 1.7 times 10 to negative 5. So what that's really asking in green here is how much PbCl2 will dissolve into a sodium chloride solution already containing chlorine ions. So we know, here's a couple things. We have to think about this for a minute because our sodium chloride has dissociated into its sodium ions and our chlorine ions. And it's a, let me get a color here. It's a 1 sodium chloride solid molecule gives us 1 sodium ion and 1 chlorine ion. Wow, that looks great. So what this means is that because we're already in we are already in a solution containing chlorine ions. It has 0.2 mole per liter sodium chloride. When that dissociates, 1 sodium chloride gives us 1 chlorine ion. So the initial chlorine ion concentration is going to equal the concentration of our sodium chloride, and that is 0.2 mole per liter. We want to know molar solubility. You already know how to calculate molar solubility. You know you need an ice table. So we're going to make an ice table, but we are being asked the molar solubility of PbCl2. So it's the PbCl2 that goes in the ice table in equilibrium with its ions. Be careful. It's not the sodium chloride. It is asking for molar solubility of PbCl2. Maybe I will do something with that so you can see. Come on. All right. I need a new color. Maybe this one. Okay. Molar solubility of PbCl2. So it's the PbCl2 that goes in the ice table. All right. We know because we're dealing with KSP that we do not need any information for the solid. We know that our lead 2 chloride dissociates into a lead ion and 2 chlorine ions. We're putting our lead chloride solution into sodium chloride, so into water with salt dissolved into it. We want to know how much of the lead chloride is going to dissolve. So the initial concentration of our lead ion is 0. There's no lead in the existing solution, but there is chlorine ions in the existing sodium chloride solution. And we know that it equals the concentration of our sodium chloride. So there's 0.2 mole per liter sodium chloride. So that means there's 0.2 mole per liter chlorine ions already there. So the initial concentration of the common ion is 0.2. That's really important for the common ion effect. This is a new piece. We actually have some chlorine ion existing already in solution. And then we just go through the normal steps for an ice table. We're going to gain some lead. We're going to gain 2x for chlorine because there's 2 chlorine ions coming out of 1 lead chloride molecule. And so in equilibrium, we're going to have x Pb and 0.2 plus 2x chlorine. So now these steps just look exactly like we've seen them before. We want molar solubility, so we're going to solve for x using our KSP expression. So KSP, concentration of lead times concentration of chlorine at equilibrium, but that squared comes here because of the 2. Maybe I will highlight that for you. Okay, so remember that 2 is here, 2 is here. So you're always going to start by writing out your equation for KSP and then substitute everything in. Now, you don't have perfect squares here, so you are going to have to check for 100 rule. So you're going to do that calculation, chlorine ion over initial chlorine ion concentration over KSP. So 0.2 divided by KSP. Here's our number. We see it's greater than 100. So that means we can ignore this 2x due to the 100 rule. So then I usually like to make a statement. And if you want good communication, you're going to make this statement. Since chlorine ion initial concentration divided by KSP is greater than 100, then you can rewrite your equation and it's going to look like this. So our KSP is still there. We're still x for the lead, but we've ignored this 2x, so it's 0.2 squared. So now this is something we can deal with. I would rearrange for x first. So x equals 0.7 times 10 to negative 5 divided by 0.2 squared. And that's some pretty simple math. We're just solving for x, and that's giving us our molar solubility. Don't forget your units and a therefore statement. Okay, so that is the last type of KSP problems we're going to look at. The biggest thing here with the common ion, and I'm going to zoom out. The biggest thing with the common ion is that now you are using an ice table. Oh, weird. Now you're using an ice table that has some existing chlorine ion for initial concentration. So this is the new piece. It's constant. This concentration is coming from the existing solution we are adding our solid into. All right, so give some practice on this, and make sure you come and talk to me if you have some questions, and we'll do a check-in.